one is easy, right? Each time n increases by 1, it increases by 1. 4, 5, 6, right? How do I manage the numerator? Now, from here, this 1 factorial, this is 2 factorial is 1 times 2, and therefore is 2. Is that right? Now, in going from 2 factorial, which is 2, to presumably 3 factorial, what's the I mean, this is 1 times 2 already, right? This one is 1 times 2 times 3, so we have an extra factor of 3. So all you have to do is take this one, multiply by what? 3. 3. You get 6. And next one, you multiply by what? 4. So 24. Next one, you multiply by what? 5. 120. And therefore, the fifth term actually is 20. Right? All right. So that's not too hard. Just assuming that you feel comfortable with notation factorial. Number 3. First term is 1. 1 as well, right? What is the next one? 2. What is this term? Next one? 3. Because according to this, starting the third term and onwards, the nth term is the sum of the previous 2 terms. Right? That's what it's trying to say. So when it comes to this, you look backwards, 2 terms, and then sum them together. Next one, comma, look backwards, 2 terms, sum them together, 5, and so on. Next one will be 8. Next one will be 13. So this one is a famous Fibonacci sequence.
It's like the nature one, isn't it? Like,
yeah, it's talking about. Actually, there's an end of section exercise problem which I didn't assign. I think it's exercise 83. If you're interested, look at 83, and it has to do with reproduction of rabbits. Let me read. It says, Fibonacci posed the following problem. Suppose that rabbits live forever, and that every month each pair of rabbits produces a new pair, which becomes productive at age 2 months. And so, question, if we start with just one newborn pair, start from that one pair, how many pairs of rabbits will we have in the nth month? That's the answer. Okay, and then what you're asked to do is to prove it. It's not, you don't need any fancy tool. You don't need any calculus or anything. Just think about it, and you convince yourself that you end up getting this. Right? I didn't assign that one, but if you're interested, look at that. So this is Fibonacci sequence. If then I ask you to do number 4, A1 is equal to 2, A3 just to make A2 is equal to 5, and AN is equal to 2AN minus 2 plus 3AN minus 1 for n greater than or equal to 3. What would you say? The first term is 2. Second term is 5. What is the next term? Try to understand the statement. Any nth term has to do with the one before it and the one before the one before it. And then, you take this one, multiply by 2, take this one, multiply by 3, add them together. What is that?
19.
19. Then move on to this one. Take 2 terms before, multiply by 2, that's 10. 1 term before, multiply by 3. What is that, 57? And then add them together. What do you get? 67. And so on. Alright, so you have to learn to understand this kind of description. It shouldn't be hard, but you just have to get used to it. Get used to this mode of description. Alright? Okay. All right, so this part is easy. Now comes limit. So let's go back to last semester. If I tell you 1 plus x limits x goes to infinity, what would you say? 0. Okay. If I then tell you limit x goes to infinity, okay, 2x over 1 plus 2x, then what would you say?
1.
Huh?
Equals
1.
1.
So that much you're familiar with, right? Okay. Now here it comes. Limits. Limits of sequences. Open an example. Let's say an is equal to 1 over 1 plus n. Then use your intuition. If I say something like this, n goes to infinity, an, what would you say this one is? 0. Because it means that if you talk about that sequence where the nth term is 1 over 1 plus n, then if n keep growing and growing and growing, what's the tendency, right? Does the individual terms approaches something? The answer is yes, it approaches 0. And likewise, if I ask you, limit, example once again, motivating example, if an is equal to, for example, something similar to that, then if I then ask you, limit n goes to infinity 2n, 1 plus 2n, what would you say? 1. Right? So now here comes formal definition. I understand that. How many of you last semester? Okay, just how many of you? You must all have taken Calculus 1, right? Okay. So how many of you in Calculus 1 have actually working experience with epsilon and delta? Raise your hand. Raise your hand. Hi. Okay. Only less about, I think fewer than 10 of you, right? So now the epsilon delta formulation is to make precise what we mean by limits. Because the concept of a limit, in calculus, unlike in algebra, a lot of quantities are not defined in a very straightforward manner. For example, derivative, what is derivative? Well, you say the slope of the tangent line, but then you say, well, what is a tangent line, right? Yeah. And so you'll be forced to do something like a limit kind of thing, right? F prime of A is equal to, as you recall, what is that? H goes to 0, F of A plus H minus F of A over H. Mm-hmm. Is that right? Mm-hmm. Okay. But then you say, okay, what do you mean by limit? Right? Then the modern way of by that modern means about 200 years old. Right? Modern way of doing it is use the epsilon delta stuff. And so if you have never used that, then in this section you're going to use it in this context of sequence as opposed to a usual function, even though I mean, you can think as, again, the sequence can be thought of as a function from n to r, but not from r to r, right? So, but still, it should be very similar. So the experience that you gain over here can help you understand the epsilon delta formulation if you need to learn it later on. So we're going to formalize it. Limits of a sequence. So let's A1, A2, A3, dot, 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 be a sequence. Let's L be a number. We say limit n approach infinity of an is equal to L if the following situation is true. Okay? If this. If for any given epsilon greater than 0, any positive number, give me a challenge in the form of a positive number, supposedly small. And I don't care how small it is. The smaller number means a greater challenge. Give me a challenge. Then I'll meet that challenge with a response. Okay, so if for any given epsilon, the epsilon greater than 0, there is n, there is a natural number n. So give me the epsilon, then I'll meet that challenge with a response, which is a natural number capital N, right? Which will do what job? Such that for all index n greater than that response n, we have an minus L absolute value is less than epsilon. So let me draw a picture to try to show you what's going on here.